So I'm going to go over some calculations on Lab 13, the last lab of the semester, as we aren't doing Lab 14 this semester. So conservation of energy is the lab that we're looking at, and this pertains to information we learned in Chapter 7. So I want to point out before I get started and show you the calculations in case you have any questions upon what you need to do and what you need to not do. So the very first page you need to complete in its entirety. I'm going to go over trial 1 and fill in the blanks that you need to fill in on part 1, that data table, and then you will go on your own and fill in trial 2, the table. After you fill in that table, then you need to do the calculations, the rest of the calculations on that page. So numbers 1, 2, 3, and 4. Okay, I will also show sample calculations of those as well, so you can fill those in accordingly. When you flip the page over, we are not doing the entire next page. So part 2 data, you do not need to do. You don't need to do 8, 9, 10, or 11 either. However, there is one more page of the lab, and I want you doing number 13. So you'll notice when you pull up that data sheet that I have attached, 12 is crossed out, 14 and 15 crossed out, but you do need to do number 13. All right, so if you have any questions on parts of this that need to be done, or if you want to do a virtual meetup or send me an email, I'm more than willing to help. So let's look at now some calculations with the table so that you know what you need to fill in and how you can fill those in, where you get the information to fill them in at. So here's our partially filled table of trial 1. Okay, so make sure to fill this in and then do trial 2 on your own as well. So you are given mass of the first cup, and by cup I'm talking about that calorimeter. So when you watched the video and you saw Dr. Rennie, he had 2 styrofoam cups. One had hot water, one had cold water in it. Those styrofoam cups are called calorimeters because they reduce heat loss and heat gain. That's why we use styrofoam cups. Oftentimes, like Sonic uses styrofoam cups to avoid your beverages from getting warm or from the ice melting. So we have 2 cups, one with hot water, one with cold water. So we massed that first cup calorimeter when it was empty and dry. It was 4.5 grams. Then he massed the cup with the cold water in it. So what number 3 in the data table is asking for is, what's the mass of just the cold water? Okay, so to figure out the mass of just the water, we need to take this 102.4, which is the cup and the water, and subtract away just the mass of the cup. So if we take number 2 and subtract number 1, that will give us the mass of just the cold water. So I'm going to take the 102.4, which is the mass of the water with the cup, and subtract out just the mass of the cup. Of course, I forgot my calculator. And I get 97.9 grams. So that's how much cold water I have, is 97.9 grams. All right, so I'm going to keep moving down. Now, in number 4 here, I have the mass of the second cup. Notice it's the same mass because they're both styrofoam cups with similar masses. And then I added hot water to that second cup for a total of 85 grams. Okay, well, it wants to know in number 6 here, we need to fill in the mass of just the warm water. So we're doing the same calculation we did up here. We're going to take the data from 5, which is cup with the warm water, and subtract the cup, which is number 4 here. So that gives me 85 grams. Cup with warm water, subtract out just the cup, which is 4.5 grams. And we get 80.5 grams. So 80.5 grams of warm water. So we are taking 80.5 grams of warm water and mixing it then with that 97.9 grams of cold water. Okay, so we mixed them together, stirred them for a little bit, and then took the final temperature. Now notice, in your table, I left out columns 7 and 8, or not columns, rows 7 and 8. Those are the temperatures of the cold and the temperatures of the warm. Now, before we mixed the warm and cold together, we took the temperatures of both of them right before we mixed them together. By doing that, we get a more accurate temperature. Because if we were to take the temperatures of the hot and the cold and then go weigh them and do other stuff, what's happening is the hot one is losing heat and the cold one is gaining heat. So their temperature is changing. So it's important that we took the temp of these two right before we mixed them so that no heat was lost. So we're getting a more accurate data. Okay, so we took the temperatures, we got 82 degrees Celsius for the warm one and 23 degrees Celsius for the cold one, and all that's in that data table. So what number 10 is asking is, what is the change in temperature? So to figure out the change in temperature of just the cold one, we're going to take the final temperature, which is 50, after we mixed them together and they convection occurred and heat was transferred, we got a final temperature of 50 degrees. So we're going to take that final temperature and we're going to subtract the initial temperature of the cold. So final temperature I just said was 50. The initial temperature of the cold was 23. And we get 27 degrees Celsius. Okay, so now let's figure out the change in temperature of the hot one. So remember, change in temperature is always final minus initial. So we're doing the same thing that we did to figure out temperature of the cold. It's just the initial is going to be different. So we're going to take that final temperature, that 50 degrees, we're going to subtract the initial temperature, but make sure we're using the hot one since they're talking about the warm water. Okay, so final temperature is 50. The warm water initial temperature was 82, so we're subtracting 82 here to get a total of negative, notice it's a negative number, so you want to keep that negative sign when you put it in the table, negative 32 degrees Celsius. All right, so now that my table is filled out, I can move on to complete numbers 1, 2, and 3. So these data calculations here for trial 1. So I'm going to go through and show you how to do that for trial 1, and then you will just copy for the next trial. So let me erase this so I have room to show those calculations. So for number 1, it's asking for heat energy lost. So remember, when we calculate heat, that's a Q value. So this is, I'm going to say Q lost. So if we're talking about the heat energy lost, what we're calculating is the Q value of the hot. So how do I know that? Well, because the warm one is the one that's losing heat. So it's the one that lost heat energy. So it's looking for the hot one here. So let me just write my equation before I continue on. So since I'm using hot, I'm going to do mass of the hot water. C, that's my specific heat of the hot water. And then my change in temperature of the hot water. So my Q lost, I need mass times C times delta T. But make sure that you are using the values of the hot water in each of those. So let's look through this table and find those values. So mass of hot. So moving down, I have mass of cool. Nope, that's not the one that I need because I'm looking at the one that lost heat. So keep going. Mass of warm water. So that's the mass I want to plug into this table. Okay, so I'm going to use 80.5 as my M sub H. C value, well, in both of these, the specific heat is of water, so it's just going to be 1. Okay, so that C value will be the same for both calculations. So I'm just going to plug in a 1 there. All right. Now for my delta T. So we already calculated delta T in 10 and 11, so we don't need to do it again. We just need to figure out which of these values is the delta T of the hot. And it's going to be number 11, the warm one. And it lost heat, so that's why it's a negative 32 degrees Celsius. So that makes sense. So we're going to take that value and plug in for our delta H. So negative 32. It's one thing I have not calculated yet. So count my calculator, we have 80.5 times negative 32 times 1, of course. And I get negative 2576. I'm not going to worry about sig figs here in lab. So, units on Q. Units on heat. It's an energy. Most energy is measured in joules, but in this course, there's exceptions to every rule, and it's going to be calories for Q. Okay, so this value we're going to compare to the heat energy gained. Because remember, we said that heat energy is conserved. So that means that our heat energy lost should be equal to our heat energy gained. They're going to have opposite signs, but they're going to have equal magnitude. So we should be somewhere in the 2000 region when we calculate our Q gained, which is what number 2 is asking for, heat energy gained. So let's do this in a different color, try to keep these a little less confusion here. So I have Q gained. So this is going to be the cold water one because the cold water is gaining heat. So I'm going to put mass sub C for mass of cold water, specific heat of cold water, and then temperature change of the cold water, because the cold water is the one gaining. So now let's find this information in our table. So mass of cold water going down, that's number 3 here that we calculated. So it's 97.9. I'm going to multiply that by the specific heat of water, which is just 1, and then by the change in temperature of the cold, which we calculated down here in number 10, delta T of cool water. That's going to be that 27 degrees Celsius. All right, so let's calculate this out and see if heat energy was conserved. And we get this time a positive number because the energy was gained, but it is 2643. Units on it are calories. So comparing these numbers, they're very close to each other, right? They're both in the 2000 range. One is positive, one is negative. So what the very last calculation, number 3, is asking you to calculate is the absolute value of the sum of these two. Okay, so what does that mean? Let's use a different color, write this equation out, and I'll show you how to use it. So we have absolute value, which means it's going to be positive no matter what. If you get a negative, just change it to a positive. And the energy gained, that's the Q gained. Plus the energy lost, which is the Q lost. And it should be a very small number because these are equal and opposite, so they should cancel each other out since energy is conserved. Okay, so let's fill in and see. If I take my gained, that's the 2643, and I add it to my lost, don't forget the negative sign, so negative 2576, I get a total of, so minus 2576, 67.3 calories. So overall, not very bad. They're very close in magnitude to each other. So what I want you to do now is make sure you're filling out what we just did in trial 1 and that you show the calculations for trial 1 that I just showed here. Now go on to trial 2 and do the same calculations, making sure to fill in the table in the appropriate spots that I've highlighted in green here, and then do the following calculations for trial 2 as well and see how they compare, if the energy was conserved or not in trial 2. Now of course it wasn't completely conserved because, I mean, those styrofoam cups, they didn't have lids on them, it wasn't a closed system. There was a little bit of heat escaping and a little bit of heat being gained in the cold one. So there's always a little room for error, is why it's not perfect under experimental conditions. Don't forget to also answer number 13 as well once you complete those. So let me know if you have any questions.